Hey, good morning, everybody. All right. Well, we're just going to go ahead and start with our faithful five people here. So let's begin with any questions. Questions on the homework, or questions on Lab 3 in particular. So I'm going to go over programmable logic, which will be those last two questions on the homework, 10 and 11. But you should be set for the others. But if there's questions, let's go over them now. I've gotten some Lab 3s turned in already, which is great. Always good to get that stuff done sooner.
I have a question on Lab 3.
Okay.
For numbers, I think 4, 5, and 6.
You talking about the steps?
ELS and SOP.
Mm-hmm.
Do you want us to create 6, one for each of the outputs tables?
You're going to have, you can do one truth table that lists 6 outputs. Right, so that's you know, here's our west, south, and east lights. And you can have green south, red south, green east, green west, red west. Whatever order, doesn't matter. 8 rows, 8 different rows, 6 columns, 48 output values, right? So this is basically 6 truth tables, but you can write it as a single truth table, right, that lists each of the output values. And then you want to write 6 unsimplified equations. Green south equals blah, red south equals blah. These have to be, in the first case, sum of product expressions from the truth table. Now you may note that red south is just the complement of green south, but that is not an SOP expression. You need to write red south equals and write the min term for each place where red south should be a 1. So you're going to end up with 6, in the first case, sum of product expressions. And then you're going to sketch a single circuit that generates those 6 outputs from these 3 inputs. And then you do the same thing again for product of sums. And then you look at those 2 circuits that you came up with, you look at the equations, you think about the process of going through those steps, and you make a decision. And say, I'm going to go with sum of products, or I'm going to go with product of sums. And you explain your thinking or feeling for why you're making that decision. And then you toss the circuit and equations that you already came up with. You go back to the truth table and you minimize your equations. So you do a K-map and you come up with a simplified green south equals, red south equals, and so on and so forth. And at that level, you can do something like, once you've generated the green south, just run it through an inverter, that's your red south, right? But that's not until your final design where you're allowed to simplify. So these earlier steps, stick with the unsimplified, just a straight sum of products or product of sums. So that's steps 3 through 5. How would you make a circuit that uses multiple equations? So, let's do an example. Let's suppose that we're coming up with, so we've got A, B, C, and we've got 2 outputs, X and Y. And suppose we come up with X equals, A, B bar, C, or B, and Y equals A, B, or AC. So we can do this. Take your inputs, run them vertically, run each one through an inverter so we have both the true and the complemented versions of our inputs available. And then start piecing them together. So to generate X, we need to take an AND of A, B bar, and C. So let's take A, B bar, C, and those together. We also need to take B, and then we need to OR those. There's X. To generate Y, we need to take A, B, thank you, and those together. And then we need to take AC and those together. And then OR those. There's Y. And you can keep going, and you can do that for all 6 outputs. And that's probably the least error-prone approach. Now, I might, see there's an AC here and an AC here, and I might generate that and run this into an OR gate and run this into an AND with B not. And that, might end up using fewer gates or something, but this is a very sort of mechanical way to go from an equation to a circuit, and it's a very easy way to error check. If something's going wrong and Y is not doing the right thing, I can go back and I can pretty easily confirm whether or not Y matches this equation. So I suggest, doing it like this. Run your inputs vertically, make their complements available, and then just come across into the logic gates. And for a product of sums, right, this level is OR gates and this level would be AND gates, but it's the same approach basically. On homework 3, what does the squares before the logic symbol mean? I don't know. Let's see what homework 3 looks like. Which question are you looking at? 3U. You talking about the circles? The circles are inverters. So this is the complement of D going in. So this function here is to take C and not D and then NAND them together. The AND gate with the circle on the output is a NAND operation. But you can also have circles on the inputs, which means there's an inverter going into that input.
Yeah, sorry. I understand that portion. I guess I was looking at 3S. Right above it, you can see that there's like little squares before the logic symbols.
Oh, so this is saying Z is going into both of the inputs. It's the wire breaking off into 2 directions.
Oh, okay, yeah.
Yeah.
Oh, yeah.
It looks like a square, but it's really just the way it's wired. And that's a useful thing to do because remember we looked at say a NOR gate, and if you put X into both inputs, the output of a NOR gate is just the inverse. So that's an easy way to make an inverter. If we take X and we NOR it with itself, well, we know X or X is just X. That's just going to give us X bar. So those things are basically inverting Z, inverting W. Cool. Other homework questions or lab questions? On question 4, what does W mean? Well, W would just be another variable, but question 4 is not assigned because we have not talked about compressed K-maps and I'm not planning to. So 4 is not one of the assigned questions, and 5 is not one of the assigned questions either. But the idea here is that we can take a truth table and we can write it in terms of other inputs. That's called compression, and we'll touch on that later on, but those questions aren't part of the assignment. Did we cover the material for question 1 on homework 3? We kind of did this in the very first homework set when you were looking at, the number of pieces of art. You had 2,500 pieces of art and you wanted to categorize them. How many bits did you need? It's kind of the same kind of thing. So, determine the number of unique functions possible with n independent variables. So, suppose you have 3 variables. So let's just call them A, B, and C. And you've got some function. And so you've got 8 rows to your truth table. And your function is determined by what the function values are for each of these rows, right? So the question, how many different functions are there of 3 variables, is the same question as how many different ways can I fill in this truth table? Which is the same question as how many different ways can I write 1s and 0s in these 8 positions? So each function corresponds to basically an 8-bit number, where the 8 bits are, the values for each row of the truth table. Well, how many 8-bit numbers are there? How many different ways can I write 8 1s and 0s? All right, 2 to the n. In this case, 2 to the 8th is 256. So there's 256 different 3 input functions. If you only had 2 input variables, right, you've got 2 inputs, you've got a total of 4 rows, which is 2 squared. And so you have 4 output bits to specify, so you have 2 to the 4th possible functions, which is 16 in this case. So this 8, this is 2 to the 3rd. This 4, this is 2 squared. So if you have n variables, you have 2 to the n rows, and you have 2 raised to the 2 to the n functions. And so that's what the solved version is doing, right? If you have 2, the number of different functions is 2 raised to the 2 to the n, 2 raised to the 2 to the n, and so on. So number of unique functions possible with n independent variables, 2 raised to, 2 to the 6th or 2 to the 7th. But then part B says, suppose a function and its complement are considered the same. How many unique functions are possible? And this is a kick back and think about it question. Suppose that, 2 variables, A and B, and suppose I have some function, whose truth table looks like that. This part B question is saying, suppose I have another function whose truth table is just the opposite. Each bit is the complement, right? We're going to treat these as being the same function. So if we do that, how many different functions are there? So it's going to be fewer unique functions, because something that produces blah and something that produces the complement of blah, we're going to treat them as the same. But that's a, like I say, kick back and think about it. It's a logic type question. What does XOR output on question 2? So an XOR is like an OR, but only one of the inputs can be a 1, so remember, this looks just like an OR, except if both inputs are 1, it outputs a 0. And so that's an XOR. And it looks like that. And remember, we also did the XNOR, which is the complement of the XOR. And so it just looks like that. Thank you. So XOR is exactly like an OR, except if both inputs are 1, the output is a 0. X NOR is the opposite, and we observe that the X NOR is also true whenever A is equal to B. So exclusive NOR is sometimes called an equivalence function. It tells you if the two inputs are the same as each other. And this is just an XOR with a bubble on the output. All right, good. Other questions? So 3 is using this universality of the NOR gate and the fact that you can make inverters, and so you can turn a NOR into an OR, and you can use De Morgan to change between ORs and ANDs, and so try to redraw this circuit using only NOR gates. So how do you do that? Well, probably a good first approach is just write an equation for this output in terms of A, B, C, D, and then maybe simplify it to give you less work to do, and then go ahead and use your NOR gate to make your inverters, your ORs, your ANDs, and your NANDs, and go from there. 4 we skipped, 5 we skipped, 6 we skipped, and then 7 we start talking about multiplexers and demultiplexers. And there is no trick to these questions. It's a matter of just kind of brutally looking at what a demux does, right? So this is a 3 input, 8 output. So one of these outputs will be driven based on which inputs are 1 and 0. And these are OR gates with some inputs inverted. And figure out what F0, F1, F2 do in response to the inputs. Make yourself a truth table or something. And there's an example up here. And then question 8, exactly the same. There's no trick here, right? This is a multiplexer. The two select lines choose one of these inputs to send to the output. How is that choice made? There's a function table right here. If S0 and S1 are both 0, the output F will be equal to D0. Well, what is D0? D0 is just A0. So you can fill in a truth table here, saying based on the value of S0, S1, what is F? Well, if they're both 0, F will be A0. If they're 0, 1, F will be A1. If they're 0, 2, F will be D2, and D2 is connected to ground, so F will be a 0. And if S0, S1 are 1, 1, F will be D3. D3 is connected to 5 volts, F will be a logic 1. And so you can write F in terms of S1, S0, A1 and A0, and S1, S0 are just fed from AB. So you can think of this as a function of AB, A1, and A0.
Yeah, I had a question.
Yeah.
So, just going back to 7U, is that multiplexer supposed to select one output? So if it was 0, it would select either 0 through 7.
So as long as the enable input is low, which it is, right? So this doesn't affect anything. If A, B, and C are all 0, then the assumption is M0 is going to be a 1, everything else will be a 0. If A, B, C were all 1s, then M7 would be a 1, everything else would be a 0. So exactly one of these output lines will go high, all the others will stay low. The line that goes high is based on what the values of A, B, and C are.
Oh, yeah. Okay, that makes sense.
And they're labeled M0 through M7, which is our notation for min terms. So that's why we believe M0 corresponds to A bar, B bar, C bar, and M7 corresponds to A, B, C.
Yeah, that makes sense.
And I think it's 7U that has a typo in it, which you should not treat as a typo. Just treat the circuit exactly as it is. But it makes the circuit kind of weird. It doesn't actually do a whole lot that's terribly useful or interesting. That's okay. Just take this circuit as correct and run through the analysis. And the goal is the analysis part, not really, knowing what the circuit does in the end. It's how you get there that's beneficial. All right, and then question 9, you've got compact forms for sum of product expressions, so you know how to write either truth tables or equations from these expressions. And the goal is to write equations for F1, F2, and F3 simplified, right? So lowest number of literals. Literal is just an expression. But it says, in addition to minimizing each function, look for shared items between the functions. So if you were actually building a circuit that was supposed to produce all 3 of these outputs, and let's say, F1 had to calculate, A bar, B bar. Well, if F3 also needs to calculate A bar, B bar, you don't need to calculate that twice. You can calculate it once up here and use it in the part of the circuit that generates F3. So this is saying look for shared items, shared terms between the functions. So taking that into account, what's the smallest number of things you have to calculate? AB, A bar, B bar, AC, C bar, B, A bar, those kinds of things. What's the smallest number you can get away with? So it's not something that we have a procedure for. We have procedures for writing these, as a sum of products. We have procedures for minimizing these using a K-map, but this is asking you to go beyond the mechanics of those techniques and look at these equations and think about, if you had to actually build this, what's the least amount of hardware you might need by trying to get creative with reusing terms between functions. And this is moving us into the next part of the course, which I believe we'll start on today, where we're going to be getting into more complex circuits, but we're going to eventually move to where we're creating very complex circuits. We're going to start off by analyzing these more complex circuits, but then we're going to move into creating these more complex circuits. And this is going to be another big bump in sort of the intensity / difficulty level of the material. Usually when we learn things, we learn it in 2 pieces. First, we do an analysis part, where we're given something and we try to understand it. And then we try to do a synthesis part, where we say, okay, now I want to create something that does this. How do I do that? And most subjects that you encounter will build in this direction. When you do physics, you'll start off by looking at systems and seeing the analysis of a system and trying to understand that analysis. And then you'll have to come up with your own analysis of a system. And it's this move from seeing something and understanding it to creating something. It's the same thing in programming. You can look at examples of code and understand what that code does, and then you need to move up to a level where you're actually creating code yourself based on what you want it to do. And so we're going to see that jump very clearly in the next unit of this course, where we're talking about state machines, machines with memory. But we've already seen that, in the circuits we worked with. First we looked at truth tables and understood what they did, and then we moved on to saying, okay, so I want to build a circuit that controls a traffic light, right? What should the circuit look like? How do I build it? And so that's the system diagram, the truth table, the equations, the simplification, the circuit, and so on and so forth. So we're going to keep going between these 2 levels. And so this is more of kind of the synthesis skill set. All right, and 10 and 11 we're going to talk about in a little bit today. Any other questions? All right, let me talk about two more more complex logic gates available. The 74138 and the 74148, and then we'll talk about programmable logic. But we started talking about multiplexers and demultiplexers, and so I'm back on the ENGR250.com, the component specifications page, and 74138. This is a demux, and it's a 3 to 8 demultiplexer. And so let's just take a quick look through the data sheet, because there's things in here that we'll see again and again in data sheets. So you know, this is the overview / sales pitch, right? Features and so on and so forth. But it's a 3 to 8 decoder. And if you know what a decoder or a demultiplexer is, that probably tells you all you need to know as far as, do I want to keep reading this? All right. There's one data sheet for a lot of different devices. There's a 54LS138. There's a 74LS138 with all of these different extensions on the end, which have to do with types of packages and so on. Thank you. And then there's the 139, which is a slightly different version, but these are close enough that one data sheet can tell you, you know, what you need to know about both of these. I want to look at the 138, not the 139. The 139 looks like it has two separate things inside. The 138 is a single thing. So let's look at that one. And we're not going to worry about, you know, these details. These are basically, you know, don't use this in your Igloo, or if you're playing in Lava, and you know, treated nicely voltage wise, 0 to 5 volts, etc. But let's look at the behavior of the 74138. So the inputs are listed in two groups. One is called enable, the other is called select. And in these truth tables, an X means don't care. An X is saying it does not matter what, for example, the C input is. And so these first two rows are sort of uninteresting. This is saying that if G2 star, whatever that is high, it doesn't matter what A, B, C, or G1 are. If G2 star is high, all of our outputs, Y0 through 7, are going to be high. And the second row says if G1 is low, it doesn't matter what G2, C, B, or A are, all of the outputs are going to be high. And these are in some sense a disabled state. And a lot of these more complex devices have a mode where you can put them into basically a do-nothing state. Now normally this is going to do something that we call decoding or demultiplexing, and the outputs will change depending on the values of A, B, and C. But sometimes we want this device to just kind of stand aside and not get in the way. And we can do that by making G2 star high or making G1 low. And the do nothing state has all of the outputs going high. And if we were to do a system diagram for this, it might look something like this. There's a G2 star, there's a G1, here's an A, B, C going in, and here's 8 outputs labeled Y0 through Y7. So G2 star, G1, A, B, C are inputs, and Y0 through 7 are outputs. And this G2 star, there's a little note down here, G2 star equals G2A or G2B. So G2 star is not actually an input. There's a pair of inputs, G2A and G2B. But they behave like this. Right, it tells us that it's an OR of these two inputs, and so if either of those inputs is high, G2 star is high. And if G2 star is high, then all of these outputs are driven high. So if you go back and you look at the actual pins on the chip, there's your power and ground connections as usual. Here's 7 of your outputs, Y0 through Y6. Here's your 7th output. Here's your selects A, B, C. But here are the enable inputs, G1, but then G2B and G2A. And so to enable this device to work, G2 star has to be 0, which means both of these inputs... Sorry, let's go back to the truth table. To enable the device to work, G2 star has got to be low, and G1 has got to be high. So we need G2 star equal to 0 and G1 equals 1. Well, the only way we can make G2 star equal to 0 is if G2A and G2B are both 0. So G1 is 0, G2A is... G1 is 1, G2A is 0, G2B is 0. So from all of that, if you actually had this device and you wanted to hook it up, what do? Connect this to 5 volts through a resistor, connect these 2 inputs to ground. And so the circles kind of, they mean invert, but they are used in kind of a funny way in these pictures. These inputs are called enable. And so G1 is an enable input. Well, to enable the device, we need to turn G1 on to say enable. So we're going to make G1 a 1. But to enable the device, G2B and G2A need to be on, but there's these little circles here. So the way we think of this is whatever value we put here is going to get inverted. Well, to enable the device, we need to set the enable line to a 1. Since these are inverted, we need to set these inputs to a 0. And so it's a little bit of a weird notation. But the other term that we'll see when we think about these things is active low. And when we say an input is active low, it means that it does its thing when the input is 0. And doing your thing depends on what your thing is. If you're an enable input, your thing is to enable the device. G1 does not have a circle that's active high, so when G1 is high, it's saying, hey, I want to enable the device. G2A and B have these circles on them, they're active low. So when these 2 inputs are low, they're saying, hey, we want to enable the device also. And so it's a shortcut for somebody looking at this picture to say, hey, to enable the device, put in a 0, and a 1. But until that sort of shorthand makes sense, go to the data sheet and look at the truth table, because the truth table will always tell you exactly what you need to know. But after you look at the truth table for a device, come back and look at this diagram, see if it makes sense. And at some point, this will start to be meaningful. Okay, same thing with the outputs. These outputs are called active low because they have circles on them. And so what's the behavior of a decoder, a 3 to 8, for example? The output is supposed to select one output based on the inputs. So if A, B, and C are all low, we should select one output, in particular Y0. Well, we normally think of selecting something as turning it on. So we would expect, from that description, that in this case, Y0 would be high, all the other outputs would be low. That would be an active high kind of situation. But in fact, this chip does the opposite. It normally sets all the output high, and whichever output you select gets driven low. So if I set my inputs to 1, 0, 1, which is the binary number 5, Y5 is selected, but selected in this case means it drives it low.
So since it's driven low, wouldn't it mean it would go through the inverter and be sent out as a 1?
So driven low means that if we think of selecting as setting something high, it goes through an inverter on the way out and comes out low. So if my input is 101 on A, B, and C, Y5 will be at 0 volts. All the other outputs will be at 5 volts.
And so they all get the inverters and then are switched, or?
Sorry, say again?
I'm just trying to understand what the end result is with the inverters also being with it on the output.
So the end result is exactly what this truth table tells you. Right? So there's no ambiguity here. If my input is 101, Y5 will be 0 volts, all the other outputs will be 5 volts. But we can infer that from the picture if we think that normally what a selector or a decoder would do is choose one output to drive high. But this particular selector has inverters on the outputs. So whereas Y5 would normally be driven high, it's actually going to come out low. And whereas these unselected lines would normally come out low, they're going to come out high. But like I say, if the circles don't make sense, don't worry about them. You never need to figure out what's going on from the circles here. You can always go to the truth table and just look at the ones and zeros or highs and lows there. But the sense of it is, normally we would select one line to drive high, to activate. The circles say these are active low, so the line you're going to select is going to come out low. And this can get really crazy. You can see, you know, circles on all of these inputs sometimes where the inputs are actually active low. And when you look at the circuit diagrams inside, sometimes you'll see, you know, a circle on each input of a gate and a circle on the output of a gate. And you can get into this thing called negative logic, and you can get into techniques called pushing bubbles and all kinds of crazy stuff. And if you're doing a lot of low-level circuit design, those become more and more important. But to use one of these devices, all you've got to understand is the truth table. And that's pretty much guaranteed to tell you, you know, exactly what the behavior is. But sometimes these truth tables are more complex. For example, the fact that they list G2 star as an input, and there is no input called G2 star. There's just a G2A and a G2B, so you have to do this operation in your head to know what G2 star is going to be. So yeah, if G2 star is high or G1 is low, all the outputs are high. But if G1 is high and G2 star is low, then this thing is operating. It's not being disabled, it's enabled. And now, based on the inputs A, B, C, exactly one of your output lines will go low. And so this is the demuxer or decoder behavior that we talked about on Monday, where you choose one of your 8 outputs to activate. And then there's all the other stuff that we don't really need to worry about, but you know, here's the logic diagram for the 138. If you really had some question that was not making sense between the truth table and the description, you could go to the logic diagram and maybe figure out, you know, the answer to some question. Well, what happens if G1 is 0, right? What exactly does that do to the outputs? And you could trace it through the logic here and figure that out. And here's a funny AND gate with 3 inverted inputs, right? Well, that's a fancy way of doing a NOR operation, but. And here's an inverter with a bubble on the input instead of the output. It still acts like an inverter, but it's a different way of doing it, and it has to do with how things are implemented. We don't have to worry about that for this course. All right, so that's an example of a demultiplexer. a 3 to 8 in this case. So other questions about that? So let me show you one other complex device. This is a 74148, and this is an 8 to 3 encoder. So the other one was a decoder. This is an encoder. It's kind of like a mux, but it's actually called a priority encoder. And priority encoder does something slightly different from what we've been seeing. Bye, have a good day. So let's look at the 148. Again, there's two different devices here. Let's look at the 148, which has an A, B, and C, or A0, A1, A2, so 3 inputs, and 8 outputs, 0, 1, 2, 3, 4, 5, 6, 7. Actually, it's the other way around. And some enable lines and power and ground. So let's just go to the data sheet. So the inputs are they're just labeled 0 through 7. We could think of them as, you know, something 0 through 7. So 8 inputs, 3 outputs. And let's not worry about GS and EO. But here's the basic behavior. So there's an enable input, EI, which is right here on pin 5. All right. That's the pin that lets you take the chip and say, you know, stand aside, don't do anything. If EI is high, it does not matter what these other inputs are. All of your 3 outputs are going to go high. Don't worry about GS and EO. Right, let's just look at these 3 outputs. So if the enable input is high, all of these outputs get turned high. It ignores these other inputs. Right? So to make the chip do what we want it to do, EI has got to be low. All right, assuming EI is low, what does this circuit do? If input 7 is low, it outputs a 0. If input 7 is high but 6 is low, it outputs a 1. If inputs 7 and 6 are high but 5 is low, it outputs a 2. If all of your inputs are high except for input 0, it outputs a 7. So the purpose of this chip is to say, hey, suppose that I have 8 inputs, and they're prioritized, with input 7 being the most important input, and input 0 being the least. I want to know what's the most important input that's set to low. So if input 7 is low, tell me that by outputting a 0. If input 6 is low but 7 is not, tell me input 6 is the one that's highest priority by outputting a 1. And this is really goofy, right? Because this is outputting 0, 1, 2, 3, 4, 5, 6, 7. But if we reinterpret a low as being a 1 and a high as being a 0, then the output right here is a 7, which corresponds to line 7 being low. And the output here would be 1, 1, 0, which is a 6, which corresponds to line 6 being low. The output here, which is 1, 1, 1, would be a 0, which corresponds to line 0 is low. And that's also the output if none of your inputs are low. So this has got basically, you know, an inverted or reversed operation on the outputs as well as the inputs. And a priority encoder is something you might use inside a computer where you had multiple things happening and the CPU had to decide what to deal with. So maybe one thing that's happening is the person just clicked their mouse. Well, that's not super important to the computer. It could go do a billion things before it deals with that mouse click, and you're not going to notice. It's going to take, you know, half a second. Or it could be that, you know, a piece of information just came in from the network. Well, it's got to deal with that pretty soon, but not, you know, like right away. If it takes it a few microseconds to respond, not a big deal. Or it could be that it just got a message from the power control system saying, hey, we've lost voltage, power is running out. Well, that's something the CPU needs to respond to really quickly, because it needs to take its critical information from memory, write it somewhere non-volatile, and then do an orderly shutdown. So the signal saying power failure might be, connected to pin 7 here as the highest priority event. The signal saying the user just did something might be connected to pin 0, saying, this is a low priority event. The clock tick might be input 3, the network packet might be input 4, and so on. And then when the CPU knows that some event just occurred, it can look at these 3 values and know what the highest priority event is. So if at the same time power is failing, the user clicked a mouse, and the clock just ticked, it would look at the output of this chip and it would see 0, 0, 0 and say, oh, that's priority 7, we've got a power failure. And it could go off and process that. Does that make sense? So that's just another example of a more complex circuit. And if you look at the sort of logic diagram of the circuit, well, they didn't draw bubbles, but they drew these little funny shapes on the inputs. That shows you these inputs are inverted, and they drew these funny shapes on the outputs, and that shows you the outputs are inverted. And the enable input goes through an inverter to the enable part of the chip, which means when this is low, the chip will be enabled. And so again, if you know that symbology, you can get a lot of the information from this one picture. But you can always, just go straight to the function table or the truth table and see exactly what the ones and zeros do. And the chip saves you from having to build this monstrosity. All right, so any questions on that? You're not expected to memorize these, but they're examples of the kinds of devices that you'll be working with here and in other courses. And one of the skills you'd like to come out of this course with is at least some ability to go through a data sheet and get information out of it. At some point, you may be assigned to do something and your only documentation is going to be a data sheet. And sort of knowing the different parts and pieces of it and figuring out what you need to know is just a really good skill to have. And for 270, our whole there's a separate textbook, but the main document we're going to use for engineering 270 is the data sheet for one chip, and it's a 300-page data sheet. And that's not necessarily large. There's data sheets that are thousands of pages. For some complex devices. All right, well, we're going to keep moving on then. So let's talk about programmable logic, and this is the subject matter of questions 10 and 11 on the homework. And it comes from this idea of, suppose you want to build a circuit to perform some particular behavior. So suppose we have some function of A, B, and C. And so we keep drawing these pictures. Let me do this in pen. So we can expose A and A bar, B and B bar, and C and C bar. And you know where I'm going with this, right? So if we wanted to implement, some particular function, like, A, B bar, C, we would put an AND gate, we'd connect up to A, B bar, C, and then if we wanted to do B, we would feed B over here, and if we wanted to OR those, we'd feed them into an OR gate. And this left part of our circuit diagram is pretty much the same from one circuit to another. The place we put these connections changes, right? But we always have our inputs, we have our inverters, and then we have, you know, a bunch of AND gates. And maybe these get connected to an OR. And maybe we have some more AND gates, and these get connected to an OR. And the particular circuit we want to build is now determined by, you know, when we take the inputs from the AND gate, where do we connect them over here? And if I connect them, you know, right here and here and here, and I connect this over here, I've got one particular function. If I connect them here and here and then here and here, I've got some other function. And so imagine just drawing some lines like this. So, right, we want to be kind of lazy as engineers. And we've got to draw, you know, 10 different circuits for our homework, and we don't want to do this 10 times. So we're going to draw a picture like this. And we're going to take it to a copier. And we're going to make a bunch of copies of it. And now we get our homework assignment, and it says, you know, let's build a circuit for, you know, f of ABC equals AB or AC or BC. Alright, so here's my first homework question. Sketch a circuit that implements this equation. Well, okay, let's connect A and B into an AND gate. Let's connect B and C into an AND gate. Let's connect A and C into an AND gate. Here's my function f. Bang, I'm done. Now, my teacher might not like this, but, you know, this is a correct drawing of a circuit that implements this equation. And, you know, maybe I'd get an eraser. I'd erase this line over here that's not connected to anything. And I'd erase this line that's not connected to anything. But functionally, right, what am I doing? I'm taking input A, putting it into an AND gate, taking B, putting it into an AND gate. This output right here is AB. This output here is BC. This output, sorry, yeah, BC. This output is AC. And this is the OR of them. So it's AB or BC or AC. And the punchline here is that once I had this template to create a circuit diagram for a given equation, all I had to do was draw a bunch of dots. I just had to indicate which of these horizontal lines get connected to which of these vertical lines. And I can make a more general picture. So let me set up my inputs again. So there's A and A bar. Here's B and B bar. C and C bar. And I'm going to have a bunch of AND gates. And I'm going to, let's just say that they're like 3 input AND gates. And so on. And over here, I'm going to make some OR gates. And I'm just going to have a bunch of inputs going into my OR gates. And so on. And this is a completely general template now for sketching a circuit diagram. I can make each of these AND gates any combination I want of A bar, B bar, C bar. In other words, I can create any product term or any min terms that I want. by just choosing which inputs should get connected to the inputs of this AND gate. And then I can take any of those product terms, and let's say, you know, this is generating, you know, A, B, C, and this is generating A bar, B bar, C bar. If I want to OR those together, well, I could put a little dot right here and a little dot right here, and it would say, hey, take this term, send it into an OR gate. Take this term, send it into an OR gate. And now my output here would be ABC or A bar, B bar, C bar. And so let me just fill in the dots here. There's ABC, and there's A bar, B bar, C bar. So does this make sense so far? This is going to be like the next half hour of what we talk about. Alright, I'm taking silence as let's keep going. So if there's questions, just go ahead and ask. Or say go back or go over this again or slow down or something. Otherwise we're just going to keep going forward. So this is like a template for a general purpose circuit. And I don't need to redraw my AND gates, my OR gates, my wires, my inputs, my inverters. I just have to draw a bunch of dots. And you know, up to this point, I could do this, and I could probably turn this in for, you know, a lab or a homework assignment or something and get away with it, right? But we're going to simplify this drawing right now, and we're going to simplify it into a way that you don't want to turn in if someone asks you to do a circuit diagram. So this next simplification is only for programmable logic. All right, so I don't want you to start doing this for your circuit diagrams. If you're drawing a 3-input AND gate, you've got to draw an AND gate with 3 inputs. But let's simplify this. Since we're going to use this as a template, here's what we could do. We could take our inputs, A, B, C. Let me do it like this. So a triangle is usually, it doesn't do anything logically. It takes the input, sends it to the output. But sometimes it's something called a buffer. It increases the current of a signal. But we're drawing a triangle here so that we can draw a little circle next to it, which means let's invert this. Okay, this is not standard symbology for drawing circuits. This is only for talking about programmable logic. But if you see this notation, what it means is this line is A, this is A bar, this is B and B bar, C and C bar. And I'm going to draw an AND gate with a single line coming off. Now, there's really no such thing as a 1-input AND gate, because what would that do? If you put in a 0, you got 0, put in a 1, you got 1. This is not a physical device. It's a shorthand for when we're talking about programmable logic, which says, hey, you know, I've got multiple inputs coming here, but suppose I want to do A and B and C bar. I'm going to put a dot right here, a dot right here, and a dot right here. And that's going to mean this output is A, B, C bar. All right. Again, not a valid logic diagram. But when we're talking about programmable logic and we're trying to use this shorthand notation, instead of drawing 3 lines from here and connecting to A, B, and C bar, we're just going to draw 1 line and put our connections on that single line. And this lets us put in a whole bunch of AND gates without having to space them out because they have a bunch of inputs available. And it lets us do the same thing with the OR gates. So we can have an OR gate here and an OR gate here. And we're just going to have a single line going into each of these OR gates. And then we're going to have outputs. And by putting dots in here, I can say, hey, I want this output to be the OR of this AND and this AND. And I want this AND to be the AND of this, this, and this. And maybe I want this AND to be the AND of this and this. So it's a kind of sloppy shorthand way of describing a circuit diagram. But you know, I might only have two inputs I want to AND, so I'll have two dots on here, and I won't have a dot here or here. Or I might just want to take, you know, B bar, and so I would just put a dot right here on B bar, and the output here would just be B bar. Well, I wouldn't actually use an AND gate to take B bar, that would just be a wire. So this is some shorthand notation. But it turns out that if we think of our circuits in this way, we can get a device called a programmable logic device. And by telling it where we want our dots, we can program this device to act like a piece of circuitry. And so this type of device is called a programmable device, or programmable logic. And when we talk about programmable logic, there's two things involved. There's this region over here, which we call the AND plane. Which is where we're connecting to, you know, the inputs of AND gates. And then there's this region of dots, which we call the OR plane, where we're connecting to, you know, the inputs of OR gates. And so there's three kinds of programmable devices. The first one is called a PLA, Programmable Logic Array. And this is a picture of a PLA. It's a PLA because we can program the AND plane and we can program the OR plane. So with a PLA, the AND plane is programmable and the OR plane is programmable. There's a similar device called a PAL, a PAL. And in a PAL, the AND plane is programmable, but the OR plane is fixed. So we don't get to control the connections over here in a PAL. There's fixed connections between the outputs of the AND gates and the inputs of the OR gates. But we can control the programming that feeds into the AND gates. And then the third type of device is called a PROM. And with a PROM, the AND plane is fixed and the OR plane is programmable. So it's the opposite of a PAL. These connections are hardwired, but we can change these connections however we like. And so these are three types of devices that we can buy. Some of them cost, you know, 50 cents or something. They're inexpensive. And you take the device and you hook it up to a programmer, a piece of equipment, and you basically tell it, hey, where should I make connections in these planes? Right, if it's a PLA, we can specify connections in this plane and connections in that plane. And then you remove the device from the programmer, and guess what? It's now a piece of custom logic that does whatever you programmed it to do. Whatever functions you specified these should be based on the values of the inputs, that's hardwired into this chip now. So if you have some complex piece of circuitry like a traffic light controller with, 6 outputs that are some logic combination of 3 inputs, you could get a programmable device, load those equations into it, and it would basically perform that function, every time that you put power on it. It would take your inputs, generate those outputs. And this is one way that people can build circuits and systems without having to use protoboards or having to connect a lot of wires together to a lot of chips. You can take something that might take 15 chips and reduce it to a single chip. So if we look at the homework questions again, so questions 10 and 11. So question 10 says, show the fuse map. So, sorry, this is called a fuse map, right? Fuse map is basically showing where the dots are to connect lines to lines. And it's called a fuse map because in the old version of these devices, there were small pieces of metal connecting horizontal and vertical lines together. And to program the device, you would pick one of these pieces of metal and you'd run high current through it and it would melt that piece of metal, just like a fuse blowing. And when that metal broke, it would break the connection. And so when you first get the device, all of these dots are present, and by programming it, you can erase the places where you don't want dots. And so that's blowing the fuses. And so this is still called a fuse map, even though we don't use fuses in them now. We use semiconductor technology. So show the fuse map of a PLA that outputs the number of ones in a 4-bit input. So this is called a ones counter. And if you input a number like, 1101, that's got 3 ones. So you should output the number 3. If you put in the number 1111, that's got 4 ones, your output should be the number 4. So you can make a truth table for this, and it would be 4 inputs, so 16 rows and 3 outputs. So you'd have 48 ones and zeros in your truth table. And your equations come out, fairly interesting. So here's the solved version, right, of this question. Here's the truth table. The output is treated as a binary number that tells you how many ones you have in your input. So for example, right here, our input is 0011. We have 2 ones. The output is the binary number 2010. Here the input is 1000. That's a total of 1 1. So the output is the binary number 1001. So you take these truth tables, you produce K-maps. See you later. You cover the ones, right? And you come up with a hopefully simplified sum of products expression for what each of these outputs should be. Didn't work so well in this case with C0 because that's just a checkerboard, right? But this is a pretty simple equation. It's just an AND gate. This is a little more complex. It's 6 AND gates all ORed together. This is really complex. It's 8 AND gates all ORed together. So if you were to build this on a protoboard, a lot of circuitry, a lot of wires, a lot of chance for mistake, lots of power, physical space, etc., etc. With a PLA, right, we can implement this by just drawing a fuse map. So for example, if our inputs are all 1, we want C2 to be a 1. So we've got this output C2, and we're going to take this as the output of an AND gate, which is driven from the uninverted 4 inputs. C1 should be an OR of these 6 terms, A1 bar, B1, B0. Well, here's A1 bar. Here's A1 bar. Let's see if we can find this one. A1 bar, B1, B0. is the output of this AND gate, and so that's one of the inputs into the C1 OR. This OR gate has a total of 6 inputs, and they correspond to these 6 product terms. C0 is got 8 product terms ANDed together. 1, 2, 3, 4, 5, 6, 7. Might be missing one. And so you take each of your combination of inputs and them together and then OR those. And so all you would need is to get, one of these programmable devices, take the information in these fuse maps, load that into the programmer, which is done through software, and you would get a chip that could take 4 inputs and generate these 3 outputs to match this truth table. And I think there's a line missing in here, because there should be one more AND gate, so there might be a small typo in here. Alright, so that's 10 solved. The unsolved question you're going to do for homework, similar. So you want to make a fuse map for an 8 input lock that should unlock, meaning it generates an output of 1, only when the input is set to one of these patterns. And as I noted in Canvas, the X's mean don't cares. So if your input is 10100100, your output should be 1. If your input is 00100001, your output should be 1. If your input is 00100101, or 10100001, or 101000101, any of those 4 combinations should also unlock the circuit, and any of the 4 combinations represented by this pattern. So if the X's are 00, 01, 10, or 11, that should also unlock. So there's 9 input combinations that should generate an output of 1. So this is going to have a total of 8 inputs and 1 output. And so and you don't need to do a K-map for this. In fact, I probably wouldn't do a K-map for this, because K-maps of 8 inputs, we haven't done that. The most we can do with a K-map easily is a 4 input function, and this is an input with 8. But since we're only generating 1 output and it's only got to be true in 9 possibilities, we're only going to need to generate 9 product terms and OR those together. So we're going to use a PLA, so both the AND plane and the OR plane are programmable. So set up your AND plane to produce 9 product terms corresponding to those 9 input combinations that should unlock, and then just take those 9 outputs and OR them together, and your single output from the circuit will be the unlock signal. Alright, so that's a programmable logic array. And then question 11, you're going to deal with a PROM, which means the AND plane is fixed and the OR plane is programmable. And so what does a PROM look like? And this is actually pretty cool. So let's just do a 3-input PROM. And I'll do our old style A, B, and C. Well, if we're not allowed to configure this AND plane, it better be set up for us in some sort of useful way. Because, the person who made this chip doesn't know what we have in mind. And what if we want to generate a product term that doesn't happen to be available here? If we want to generate A, B, C bar and there doesn't happen to be a product term for that, we're done. We can't use this. So the way the AND plane is pre-programmed is to give you all possible product terms. So A bar, B bar, C bar, A bar, B bar, C, A bar, B, C bar, A bar B C, A B bar C bar, A B bar C, A B C bar, and A B C. Anybody recognize these expressions? Numbers counting up from 0. These are exactly our min terms. So in a prom, the AND plane is hardwired to generate every possible min term of the inputs. And we know from our work with sum of products that we can write any equation as a sum of min terms. So even though we can only program the OR plane, that's sufficient to let us represent any function that we want. Because if we want to generate the function M2 or M3, we just put dots right there. If we want to generate the function M1 or M3 or M4, we just put dots right here. The AND plane is big enough that it's generating all the possible min terms for us. And so to write a sum of products equation, we just pick the products we want to sum, and we say, hey, feed those into an OR gate. So just having a programmable plane over here is still plenty of flexibility to implement any function we want. So this last question, 11, is again an unlock circuit, and it's got 9 unlock combinations, but you want to implement this using a prom. And it says don't draw unused AND terms. So 8 inputs, you would have 256 rows. Don't draw all 256. Just draw the ones that you need. And there's a note in Canvas about this also, right? So if I don't need to use this term, don't draw that term in your picture. Otherwise, your picture is going to be, 256 lines of dots and AND gates. Just draw the ones that you need, and you'll only need a few of them. So draw a picture of this prom with the fuse map. Typically when you draw a picture of a fuse map, you draw an X to show that you're making a connection if it's a programmable connection. So to match what the book's doing, I should have drawn these as X's. But sorry, these as X's. So same thing, it's a connection between this horizontal line and this vertical line. But the X is basically saying this is a connection that the user is deciding to make. The dots are saying this is a connection that comes from the factory. So to make this a fuse map, really I need to have X's there instead of just dots. And if you go back to the component specifications, you can find a PAL 16L8. Here's an example data sheet for a programmable device. And it's got a bunch of inputs and a bunch of outputs and some lines that can be inputs or outputs. And there's a fuse map of sorts in here, right? So here's your inputs on the side, input 1, 2, 3, 4, 5. And these are running across into AND gates, and those AND gates get combined into an OR gate. And this has some extra functionality to it. But here's our input 2, for example, and it connects to this first vertical line. And here's input 2 inverted, that connects to the second vertical line. Input 3 connects to line 4, and input 3 bar connects to line 5. And so this is drawn, it's laid out a little differently from here where we had our inputs, you know, running up and down to begin with. This is actually feeding the inputs in from the side, but then, you know, routing them up and down. And here's the inputs to the AND gates, and then all of the outputs of all the AND gates get ORed together. So there's no programmable OR plane in here, right? This is a PAL instead of a PLA. So the AND plane is programmable, the OR plane is fixed. But in addition, right, there's the option to take the output of all of this and feed it back in through these lines to another pair of inputs. So we can have feedback in these. We could take an output and feed it back in to the input. And there's also an enable output. We don't have to worry about this yet, but this gate is one that will let us optionally disconnect the output from this internal circuitry. And so the fuse map for this is basically all of these points where things cross. And there's 32 connections on each row, and there's a bunch of rows, and so there's a total of probably 2,048 connections or so that we could make. And to program this, you would have a computer that takes your equations, generates the right ones and zeros for this, and then sends them in through, you know, a USB connection or something to the actual programmer, and that would configure this chip. And there's versions of this that have memory elements on the output, which we're going to talk about next week, and so on and so forth. So you can look at this data sheet if you want to see kind of a more real-world example of this. And I'd love to do a lab with this sometime in person. We haven't done that before, but I think it would be interesting. All right, so questions about that? Does that give you enough to tackle the homework? All right, so let's do a 5-minute break and come back. We'll talk about Lab 4. Lab 3 is due on Friday, and then Lab 4 will be due next Friday. So I want to get you started on that today so that when you're done with Lab 3, you can get going on Lab 4 without having to wait until Monday. So let's come back at about 4.5 minutes, and we'll go on to the next lab. let's see. All right, so let's talk about Lab 4. And Lab 4 is another one of these labs that looks pretty short on the surface. It's one short experiment and then a longer experiment, but there's a lot of details here. So the first experiment is to play with what's called a 7-segment display. This is a device that has 7 or 8 LEDs inside it, arranged in a way so that you can make different symbols by lighting or not lighting different ones of these LEDs. So the LEDs are labeled A through G. DP is a decimal point, we don't have to worry about that. But by lighting up certain ones of these segments, for example, if I light segments A, B, and C, we'll get a symbol that looks like, you know, a line here and then a line going down, looks like the digit 7. And if I light up all 7 of these segments, so every one of these areas is lit, it'll look like the digit 8. And so you can use this display to display different symbols on this one device. Typically numbers, digits from 0 through 9. And so your first goal is to play with this device by simply hooking up switches to either turn on or off the different segments. So here's a picture of how this gets hooked up. These 2 pins have to go through resistors to ground. These are 1K resistors connecting to ground. And then each of your switches connects 5 volts to these different inputs. And each input corresponds to a different segment on this display. So common, that's the connection to ground through a 1K resistor. And then, for example, if I put 5 volts into this pin labeled A, this segment will light up. If I put 5 volts into this pin labeled B, this segment will light up. And in Tinkercad, let me just go ahead and bring Tinkercad up. Because there's one detail on this, and if you miss this detail, it's a lot of lost time. So let's pop a 7-segment display in here. This is set up to what's called a common anode. And there's a note in here. This is a common anode 7-segment display. Common anode is the default mode, but we're going to want to switch to common cathode later. And there's a drop-down box here. You can switch this to common cathode. Common cathode means that the common line here, instead of being connected to ground, would be connected to power. Actually, do that for this one too. All right, so yeah, that's the thing to keep in mind. When you use a 7-segment, switch this to common cathode. If you leave it at the default, which is anode, none of your stuff will work. So set it to common cathode, and then this wiring diagram should work, where the common line is connected to ground. So experiment 1, you just build this circuit and flip the switches and see what happens, and record your observations. All right, and then the second part of this experiment, go ahead and wire in this chip called a 4511. All right, this is called a 7-segment decoder. And the idea of this chip is you put in a binary value from 0 to 15, and it will figure out which of these segments should get turned on or off to make this display something that looks like a digit. And so if we go back to ENGR250.com, component specifications, and pull down the data sheet for the CD4511, what it does is it basically lets you specify 4 inputs, D0, 1, 2, and 3. And based on the binary value of that 4 input number, these 7 outputs, which you connect to your 7-segment display, will turn on or off so that your display looks like this. And this is for inputs with values 0 through 9. And then for 10 through 15, they have different weird symbols for them. But we'll mostly use them with just inputs 0 through 9. And so here's your truth table, right? And if your inputs are, for example, all zeros, then every segment is lit up except segment G. Segment G is the one in the middle. So if your inputs are all zeros, all of these 6 segments on the outside will light up. The middle one will be off. It looks like the digit 0. If you put in the binary value 1, so D0 is a 1, D1, 2, 3 are all zeros, that's binary 1, you would hope the display looks like a 1, so you'd hope segments B and C will be lit and everything else will be off. Well, look at your truth table. If your input is a 1, what do your outputs do? Segments B and C are high, all the other segments are low. So the display looks like a 1. And if you put in a value higher than a 9, all the segments are off. So it only displays digits from 0 through 9. And you've got 3 other inputs, and for all of these interesting combinations, this input has to be low, these 2 inputs have to be high. So low, high, high. Alright, so go to your data sheet, figure out which pins are which, and wire up this circuit. You don't have to wire it from this diagram, right? But this should be the circuit that you end up with. But include a circuit diagram, right? Showing how you connect the different inputs and outputs of this chip to your 7-segment display. So now if you build this circuit, you should be able to flip through all combinations of inputs from 0 through 9 and observe that the corresponding digit appears on this display. And then if you input binary numbers corresponding to 10 through 15, the display should be blank. So that's kind of a warm-up for the next experiment, which is your 2-bit adder. And your goal here is to build a circuit that can take 2 2-bit numbers, add them, and then show you on this display what the sum is. So if you set all your inputs to be 0 plus 0, your output will be 0. If you set your input to be 3 plus 3, your output should show a 6. If you do 2 plus 3, your output should show a 5, and so on. Alright, got the goal in mind? Alright, so how do we do this? Let's look at a 1-bit adder. So I'm going to have 2 inputs. I'm going to call them A0, B0, and I'm going to have an output called a sum. 0 and 0 is 0. 0 and 1 is 1. 1 and 0 is 1. 1 plus 1 is a little tricky. If I do 1 plus 1, I should get the number 2, which in binary looks like this. I can't express 2 with a single bit. My sum bit would end up being a 0, but I would also have a carry, which in these cases is a 0, but in this case is a 1. So my 1-bit adder looks like this. There's a system diagram for a 1-bit adder. And if I think of the carry and the sum as being a 2-bit number, it just looks like the binary version of whatever the sum of those two bits is, 0, 1, 1, 2. But it's really two outputs, right? A sum bit and a carry bit, where the sum bit is the bit right here, and the carry bit is the bit next to it. Question, could you build a circuit that produces this carry and sum output based on those inputs? Given time and motivation, could everybody do this? Right, it's a bit rhetorical. The answer is yes, you can. Right? This is week 1 of Engineering 250. This is Engineering 120 when we talk about digital logic. This is simpler than a traffic light controller, which everybody has been able to design and come up with equations for already, right? You could do a sum of products. Your sum would be A0 bar B0 or A0 B0 bar. And your carry would just be A0 B0. So it's a few gates, it's a few equations, it's not a big deal. And you could put all of that circuitry inside this box, and now you put in 2 bits, you get out a sum and a carry. So 1-bit adder, not too bad. Let's look at a 2-bit adder. And this part is super duper critical for getting points on the lab. So a 2-bit adder is going to take 2 2-bit numbers. But I'm going to think of this as just a plain old function of 4 inputs. I ran out of space as usual. So I'm going to have 16 rows here, right? In these top 4 rows, my value A is 0. In the next 4 rows, my value of A is 1. In these next rows, my value of A is 2, and so on. My B input, B is 2 bits. This represents the value 0, 1, 2, 3. 0, 1, 2, 3. 0, 1, 2, 3. And so on. And so I can write down what my sum should be. A plus B should be 0, 1, 2, 3, 1, 2, 3, 4, 2, 3, 4, 5, and so on. Well, what's the largest sum I can have if I'm adding 2 2-bit numbers? What's the biggest my sum might end up being? Two bits, so not 2 decimal digits. So 99 plus 99 would be good for decimal, but for binary, the largest 2-bit number is 1, 1, which is 3, and so our largest sum is 3 plus 3, which is 6. So how many bits do I need to represent a number as large as 6? Three bits, good. So I'm going to have 3 sum bits. I'm going to call them sum 2, sum 1, and sum 0. And so I can write a truth table for a 2-bit adder. And it's a table containing 4 inputs and 3 outputs. And it's more work, but it's no different from any truth table we've worked with so far. I could write an equation for S0. I could write a sum of products for every place where there's a 1. I could put it in a K-map and simplify it and so on. I could write a sum of products for S1. I could write a sum of products for S2. I could come up with equations. S2 equals, S1 equals, S0 equals. I could turn those into circuit diagrams. I could build a circuit. So fundamentally, the process of building a 2-bit adder is nothing different from what I've been doing all quarter, right? It's just another truth table, another set of values. But this turns out to be a really big circuit because we have 16 rows, and S0 is going to have 8 ones in it, and so that's going to be 8 sums of products, 8 products that we sum together, and this is going to end up being a really complex circuit. Alright, so let's look at the details of Lab 4 Experiment 2. Design a 2-bit adder with a carry. Your circuit should allow for two 2-bit binary inputs, A1, A0 and B1, B0, which you're going to feed in through switches, and you're going to add them up, and since the answer is going to be something between 0 and 6, you're going to send that to the 7-segment display and display the answer numerically. Okay, that's your ultimate goal, but how you get there determines your grade on the lab, right? You have to get there through the following steps. So step 1, clearly identify the inputs and the outputs for the 2-bit adder. That's your system diagram. Well, we kind of did some of that here already for a 1-bit adder. Do it for a 2-bit adder. And your system diagram should have 4 inputs, A1, A0, B1, B0, and it should have 3 outputs, some 2, some 1, some 0. You've got to specify what those inputs and outputs mean. So specify what the inputs and outputs mean in the system diagram. For example, the way I've written this, S2 is the most significant bit of the sum, S0 is the least significant. But somebody somewhere else might say, I'm going to call this S0, S1, S2. Or they might say, I'm going to call this B0, B1, A0, A1. That's still a perfectly fine 2-bit adder, but to use that 2-bit adder, I've got to know, hey, when I get this bit S2, is that the most significant bit or the least significant bit? If I want to add the number 2, should I feed that in as a 1, 0 or as a 0, 1? So make sure you don't just say, these are inputs, these are outputs. Well, you can see that from the arrows. Make sure you specify A0 is the least significant bit. A1 is the most significant bit of A. B0, B1 are the least and most significant bits of B. The circuit adds A and B together and produces a 3-bit sum. The sum is called S. S2 is the most significant bit. S0 is the least significant bit. So you're going to have to be a little wordy, right? You're going to have all that information along with your system diagram to get full credit for the system diagram. And then a truth table based on the inputs and outputs. Basically going to be this, right? But, all 16 rows. All right. And then minimize sum of product or product of sums using a K-map for this truth table. Okay, you're going to end up with 3 equations, S0 equals, S1 equals, S2 equals. And you can minimize it, you can use K-maps, you can choose SOP or POS, but show all of your work, show your K-maps, right? And when you're done, the final part of that section would be, S0 equals blah, S1 equals blah, S2 equals blah. But don't just put these equations in. You got to show how you get there. Right? So put in all of your work, and then go ahead and state the literal count and the number of gates needed to implement each of these. So how many terms are there in each of these, and how many gates would you need to build this circuit? Alright, that's the first 3 steps. And those are going to be big and complex. And then, step 4, you're going to do something different. You're going to take a totally different approach. Step 4, you're going to use what's called a full adder, half adder design, which we're going to talk about right now. So the idea of a half adder, full adder is when we do pencil and paper addition, we are smart about it. If I want to add 1 0 and 1 1, what do? I say 0 plus 1 is 1. And I say 1 plus 1 is 0 with a carry of 1. There's my addition. And if I want to do 1, 1 plus 0, 1, I say 1 plus 1 is 0 with a carry of 1. 1 plus 1 plus 0 is 0 with a carry of 1. There's an extra 1. 3 plus 1 is 4. So for us as humans to add 2-bit numbers, we don't need to know the sums of 2-bit numbers. All we need to know is how to add 1-bit numbers, and possibly an incoming carry. So we can define a block called a full adder. And a full adder takes 3 inputs, A, B, and an incoming carry, and it produces a sum and an outgoing carry. And you can write a truth table for this. And the cool thing about full adders is if we do the following. So let's have a full adder, and let me put my inputs a little differently. And my outputs a little differently. So I'll take in A, B, and an incoming carry. I'll produce a sum and a carry out. And I put a second full adder right next to it. And I connect this carry out to this carry in. And here's another pair of inputs, A, B. And here's a sum. And here's a carry out. Well, if I take this circuit and I do the following, I feed in A0, B0, A1, B1. I feed a 0 into here. Guess what? This is S0, S1, S2. This will give me my 2-bit adder. And this is mimicking what we do when we add with pencil and paper. This will take our 2 least significant bits, add them together, take the sum bit, that's this first bit over here, and it will take the carry that's generated by this, that's this carry up here, and it will say, let's add that to the second bits. So we take that carry, we add it to the second bits. The sum bit that comes out, that's this part of our final sum. And if there's a final carry generated, that's the third bit of our sum. So we can build a 2-bit adder using a pair of full adders. And eventually we can make a further simplification by noting that this first full adder, the carry going in is always a 0. And so we're going to get rid of this and we're going to replace this with something called a half adder. So we'll go through that in detail on Monday. But for Lab 4, which you should start as soon as you're done with Lab 3, you can do these first 3 steps without knowing anything about half adder, full adder. And in fact, you have to do these first 3 steps without knowing anything about half adder, full adder. And if you do half adder, full adder stuff in these first 3 steps, you're going to lose most of the points for this lab. So you can do this first half of experiment 2 with what you already know, with what you knew week 1 basically. Right? And the goal here is to just do the usual circuit design for this kind of truth table. So, you know, draw your system diagram, complete the truth table for all 16 rows, make sure it makes sense to you, figure out what these 3 output columns should be, write each one as a function of the inputs, and then, you know, either do a sum of products, product of sums, minimize using K-maps, do a little bit of analysis on the output. Don't sketch that. Don't draw a circuit diagram because it's really going to be big and ugly and huge, right? But come up with the equations and analyze these equations in terms of how many terms there are and how many gates you would need if you were to implement it. And so I would say get through these first 3 steps. Get through the previous, you know, experiment, which is playing with the 7-segment and the decoder. And then do these first 3 steps of experiment 2. And if you get through all of that before Monday, leave it there, or go on and you know, look at half adder, full adder. But Monday we'll go into more detail about the half adder, full adder design, and look at truth tables for that, and get into more specifics. But really, really important, don't do anything with half adder, full adder up here. And I guarantee if you look online, if you look at other people's labs, you look at friends' work and so on and so forth, you're going to end up doing things in here that actually belong in step 4. And you'll lose most of the points for this experiment if you do that. So up through here, just it's a plain old sum of products, product of sums question. Does that make sense? All right, I got 3 hours of lab hours tonight. I've got 2.5 office hours Thursday. I've got an hour of office hours Friday. Lots of opportunity to come in if you got questions on this or want to go over homework or previous labs or anything else. If I don't see you in there, have a great rest of the week, and I will see you on Monday. All right, bye.